let's take a look at factoring completely problems. Factoring completely problems often involve multiple uses of the same factoring technique. So you find the difference of perfect squares a bunch of times over and over again, or some combination of factoring techniques like greatest common factor and using products or sums, or greatest common factor and regrouping. So when I'm factoring completely, it's sometimes helpful to have a list of all of my factoring techniques right there in front of me. Then if I'm kind of stuck looking at a problem, I can look at my list and say, oh yeah, maybe I should try greatest common factor or something like that. So let's start off by generating a list of all the factoring techniques that we have to date. So the first one I always write down, always try to do, is greatest common factor. That's a real easy one, and it simplifies the problem nicely. So greatest common factor. We've got the difference of two perfect squares. So difference of two squares. So greatest common factor I can use on all polynomials. Difference of two squares, I need two squares, and I have to be subtracting. So has to meet all three of those criteria. So let's see, difference of two squares, difference of two cubes, and that's just like the difference of two squares except they're cubes, right? So I've got two cubes and I'm subtracting them. I could find a factoring of the sum of two cubes. So maybe I've got two cubic terms, but I'm adding them. I could do some grouping, and some people call grouping splitting down the middle. Split down the middle. And usually I've got four terms for that. It's possible to take a three-term problem and turn it into a grouping problem, and there's some techniques for doing that. The last method that I have is something that I call products and sums. Products and sums. And some people call it unfoiling or reverse foiling. Unfoil. And that's useful if you have three terms. Alright, so we have all of these great factoring tools at our disposal. Let's use them. Let's start off with a problem like this. X to the 8 minus 1. So here's example 1. Let's go down our list. Start off with greatest common factor. Well, I don't need to use that, right, because there's nothing in x to the 8 or in 1 that I could divide out. What about difference of two squares? Well, I have two things, x to the 8. That's one term, and the other is my minus 1. I'm definitely subtracting them. Are these squares? Well, the 1 is a square. The 8 will be a square if it's divisible by 2, which it is. 8 divided by 2 is 4. And if you're not sure why that is, think about that for a second. X to the 8. If it's a perfect square, I can rewrite it as x to the something times itself. And in exponents, the rules for exponents are if you have the same base, you're going to add the exponents together. So if I had x to the 4th times x to the 4th, right, something times itself, I would find out what that answer was by saying, well, what's x to the 4 plus 4? And that would bring me right back to x to the 8. So x to the 8 is definitely a square, a perfect square. Let's go ahead and factor this. The method I'm using is the difference of two squares, and that looks like this. A squared minus b squared equals a plus b times a minus b. That's what my formula looks like. In this case, a is equal to x to the 4th, and b is equal to 1. Let's plug it in. X to the 4th plus 1, and x to the 4th minus 1. Alright, so we've taken x to the 8 minus 1, and we've factored it into x to the 4th plus 1 and x to the 4th minus 1. Now, if you're really good at factoring using the difference of two squares, you probably just go right to that step here that I just did, and you're not writing down the a and the b, but sometimes it's helpful when you have kind of funky exponents like the x to the 8, just to kind of think that through, what the what your a should be. Like, what are you going to actually put into those factored terms? Let's just take a look to see if we're done yet. All right, x to the 4th plus 1. Well, I know there's no greatest common factor. There's not going to be any that suddenly appear. It's not the difference of anything, so it's not the difference of two squares or of cubes. Is it the sum of two cubes? Well, no, 4 is not divisible by 3, so it's not the sum of two cubes. I need 4 terms for grouping, which I don't have. I need 3 terms for unfoiling, which I don't have. So x to the 4th plus 1 is done. This one is done. Done. What about x to the 4th minus 1? No greatest common factor, but it is a difference of two squares, right? X to the 4th is a perfect square, and 1 is. There's 2 of them. You're subtracting, so I can use the same difference of two squares on the x to the 4th minus 1. So this first factor is going to stay the same, x to the 4th plus 1. I'm just going to bring it right down. It's going to stay right there. X to the 4th minus 1, however, I'm going to split up into 2 more factors, x squared plus 1 and x squared minus 1. All right, let's look at the process again. X to the 4th plus 1, that's done. X squared plus 1. Look at my list. No greatest common factor. It's not the difference of 2 of anything. It is the sum, but x squared is not a cubed because 3 doesn't go evenly into it. It's not 4 terms, it's not 3 terms, so now that one's done. So this is done, now this one's done. Look at that, x squared minus 1. I'm thinking, once again, no greatest common factor, but yup, difference of 2 perfect squares. So we're going to split that up one more time. All right, let's bring down the done ones. X to the 4th plus 1, done. X squared plus 1, done. X squared minus 1 is going to become 2 more factors. X plus 1 and x minus 1. And now those are both done. X plus 1, no greatest common factor. No more squares or cubes there. Same with x minus 1. Here it is, your final answer. So I'll rewrite it so we can see the original problem. 8x to the 8 minus 1 becomes x to the 4th plus 1 times x squared plus 1 times x plus 1 times x minus 1. There we go. So you can see that I had to use multiple methods, or that same method, difference of two squares, twice. Once to get it down to the x minus 4, or x to the 4th minus 1, and then once to get it down from the x squared minus 1 down to the x minus 1. So multiple times.